to this Brayton cycle, this is the ideal cycle that is used in gas turbines. So let us see what is this Brayton cycle and what is it about. So this Brayton cycle consists of 4 processes, out of which 2 are isentropic process and 2 are constant pressure process or you can also call them as isobaric process. Now here process 1 to 2 in case of Brayton cycle is isentropic compression. Process 2 to 3 is constant pressure heat addition. Process 3 to 4 isentropic expansion. And process 4 to 1 is constant pressure heat rejection. So these are the 4 different processes that we come across here. Now let us see the PV and TS diagrams. So here is the PV diagram and the TS diagram. Now process 1 to 2 is isentropic compression. So isentropic compression, let us draw it like this. Process 1 to 2 is isentropic compression. In the PV diagram it looks like this. In the TS diagram, isentropic compression is represented as a vertical line pointing upwards like this, 1 to 2. 2 to 3 is constant pressure heat addition. So when heat is added at constant pressure, the volume increases as the temperature increases. So process 2 to 3 in the PV diagram looks like this. And in the TS diagram, you will have constant pressure heat addition like this. Then process 3 to 4 is isentropic expansion. It is represented as a vertical line pointing downwards, and here 3 to 4 isentropic expansion, and it comes like this. Now 4 to 1 is constant pressure heat rejection. Constant pressure heat rejection is represented in the TS diagram like this, whereas in the PV diagram you will get a horizontal line like this. Now these two obey PV power gamma equal to constant, as these are isentropic processes. Here we need to come across compression ratio, the first one. Compression ratio is volume at the beginning of compression, which is V1, by volume at the end of compression, that is V2. Now let us go for another ratio called pressure ratio here. So pressure ratio in this particular case is the maximum pressure, that is P2, by the minimum pressure is P1, or you can also write this as P3 by P4, because process 2 to 3 is constant pressure process, and at the same time process 4 to 1 is also constant pressure process. So in this particular case, this pressure ratio plays a very important role. Now let us see heat supply. If we consider heat supplied, so heat supplied is during process 2 to 3. So the formula for heat supplied is mCp T3 minus T2. So this is heat supplied. Then heat rejection also takes place during constant pressure process, that is during process 4 to 1. So here this is mCp T4 minus T1. This is heat rejected. Now let us see the work done. So work done is heat supplied minus heat rejected. So we can write this as mCp T3 minus T2 minus mCp T4 minus T1, or simply we can write this as mCp T3 minus T2 minus T4 plus T1. Now the thermal efficiency is work done by heat supplied, or we can write this as 1 minus heat rejected by heat supplied. So this will be equal to 1 minus mCp T4 minus T1 by mCp T3 minus T2. mCp gets cancelled. So now the thermal efficiency is 1 minus T4 minus T1 by T3 minus T2. So this is the thermal efficiency in terms of temperatures. Now let us get this same thermal efficiency in terms of pressure ratio. Now for that, let us consider process 1 to 2. If we consider process 1 to 2, this is isentropic compression, so it obeys PV power gamma equal to constant. Now from this we can write T2 by T1 is equal to P2 by P1 whole to the power gamma minus 1 by gamma. So this is the relation between temperature and pressure when we have come across isentropic process. So from this, P2 by P1 is nothing but the pressure ratio, so Rp to the power gamma minus 1 by gamma. So from this we can write T2 equal to T1 into Rp to the power gamma minus 1 by gamma. So this is T2 value. Now let us go for process 3 to 4. Process 3 to 4 is isentropic expansion, so this also obeys PV power gamma equal to constant. So from this we can write T3 by T4 is equal to P3 by P4 whole to the power gamma minus 1 by gamma. So P3 by P4 is nothing but Rp to the power gamma minus 1 by gamma. Now from this we can write T3 is equal to T4 into Rp to the power gamma minus 1 by gamma. So this is the value of T3 here. Now see, P2 by P1 or P3 by P4 both are equal to pressure ratio. That is the reason we have written like this in this particular case. Now therefore the thermal efficiency will be equal to 1 minus, you can write T4 minus T1 by T3 can be written as T4 into Rp to the power gamma minus 1 by gamma minus T2 is T1 into Rp to the power gamma minus 1 by gamma. Now from this we can write 1 minus, if we take in the denominator Rp to the power gamma minus 1 by gamma common, then it will be T4 minus T1, and in the numerator it will be T4 minus T1 only. Now these two will get cancelled, so therefore the thermal efficiency will be 1 minus 1 by Rp to the power gamma minus 1 by gamma. So this is the thermal efficiency of the Brayton cycle in terms of pressure ratio. Now we can also write this thermal efficiency in terms of compression ratio, and that is, see here, if we take process 1 to 2, process 1 to 2 is PV power gamma equal to constant. So from this we can write P1 V1 power gamma equal to P2 V2 power gamma, and P2 by P1 will be V1 by V2 whole power gamma. So P2 by P1 is nothing but the pressure ratio. So this will be equal to V1 by V2 is compression ratio to the power gamma. So therefore we can write the thermal efficiency as 1 minus 1 by Rp, instead of Rp, Rc to the power gamma whole to the power gamma minus 1 by gamma. So these two will get cancelled. So therefore finally the thermal efficiency is 1 minus 1 by Rc to the power gamma minus 1. So this formula will be similar to that of Otto cycle efficiency. So we can write like this. So this formula will be similar to that of Otto cycle efficiency. That's why we can consider writing the first point like this. If the compression ratio of Otto and Brayton cycles are same, then their efficiencies are equal. So now let us go for the second point. The second point in note, that is, if the Brayton cycle operates between minimum and maximum temperatures of T1 and T3 respectively, then the condition for maximum work done will be, now here we are considering Brayton cycle is operating between minimum and maximum temperatures of T1 and T3 respectively. Then the condition for maximum work done we are taking. Now for this we need to take work done formula. Work done is mcp T3 minus T2 minus T4 plus T1. So this is the formula for work done. Now we need to get this T2 as well as T4 in terms of T1 and T3. So then only we can determine the condition for work done, just like in the case of Otto cycle. So for that we need to use these PVT relations that we have learnt. So T2 is T1 into Rp to the power gamma minus 1 by gamma, and T3 is T4 into Rp to the power gamma minus 1 by gamma. Now from this T4 we want. So T4 can be written as, so T4 can be written from this expression as T3 by Rp to the power gamma minus 1 by gamma. Now if I substitute those values here, work done will be mcp into T3 minus T1 into Rp to the power gamma minus 1 by gamma minus T3 by Rp to the power gamma minus 1 by gamma plus T1. Now let us consider gamma minus 1 by gamma is equal to some z. Now from this work done will be equal to mcp into T3 minus T1 into Rp to the power z minus T3 by Rp to the power z plus T1. Now we can write this as mcp T3 minus T1 into Rp to the power z minus T3 into Rp to the power minus z plus T1. So taking Rp to the power z to the numerator, it becomes Rp power minus z. Now to get condition for maximum work done, we need to put dW by dRp equal to 0. That means we need to differentiate work done with respect to the pressure ratio and equate it to 0. So then only we are going to get the condition for maximum work done here. Now here d by dRp of, we can't differentiate mcp, so mcp can be removed. We need to write this term T3 minus T1 into Rp to the power z minus T3 into Rp to the power minus z plus T1 here. So this is equal to 0. Now on differentiation here, this becomes 0 minus T1 into z into Rp to the power z minus 1 minus T3 into minus z into Rp to the power minus z minus 1 plus T1 will become 0 here. This will be equal to 0. Now minus of minus z can be multiplied so that you will get a positive value. So T3 into z into Rp to the power minus z minus 1. So this is equal to T1 into z into Rp to the power z minus 1. So z gets cancelled, and from this we can write T3 by T1 is equal to Rp to the power z minus 1 by Rp to the power minus z minus 1. So taking this to the numerator, this becomes Rp to the power z minus 1 plus z plus 1. So minus 1 plus 1 gets cancelled. Then we can write T3 by T1 is equal to Rp to the power 2Z, or you can write Rp is equal to T3 by T1 whole to the power 1 by 2Z. See, this pressure ratio that we have got by differentiating work done with the pressure ratio and equating to 0, we call this as the optimum pressure ratio. So optimum pressure ratio is T3 by T1 whole to the power Z is gamma minus 1 by gamma. So if I substitute this here, then it becomes gamma by 2 into gamma minus 1. So this is the formula for condition for maximum work done. So the condition for maximum work done is this. Now let us go for the next point. The next point is, if the Brayton cycle operates between the minimum and maximum temperatures of T1 and T3 respectively, then the maximum work done will be so here what we need to consider is the work done formula is MCP T3 minus T2 minus T4 plus T1. So we need to get this equation in terms of T3 and T1. So we need to write T3 minus T1 into Rp to the power gamma minus 1 by gamma minus T4 can be written as T3 by Rp to the power gamma minus 1 by gamma plus T1. Now here, in order to get maximum work done, we need to substitute the optimum pressure ratio in place of Rp, so that it becomes T3 minus T1 into Rp value. We need to take Rp optimum, so that we can write this as T3 by T1 whole to the power gamma by 2 into gamma minus 1 whole power gamma minus 1 by gamma minus T3 divided by T3 by T1 whole to the power gamma by 2 into gamma minus 1 whole power gamma minus 1 by gamma plus T1. So these will get cancelled. We can write this same expression like this: W max is equal to MCP into T3 minus T1 into, here T3 by T1 whole power 1 by 2 will be remaining. So we can write this T3 by T1 whole power 1 by 2 as T3 power 1 by 2 into T1 power minus 1 by 2. So I am writing it like this: T3 power 1 by 2 into T1 power minus 1 by 2 minus, here T3 by T1 whole power 1 by 2 will be there. So we can write this as T3 into T3 power minus 1 by 2 T1 power 1 by 2 plus T1. Now from this we can write this as MCP T3 minus T1 power 1 minus 1 by 2 into T3 power 1 by 2 minus T1 power 1 by 2 T3 power 1 minus 1 by 2 plus T1. So finally we can write this as mcp into T3 minus T1 power 1 by 2 T3 power 1 by 2 minus T1 power 1 by 2 T3 power 1 by 2 plus T1. Now this can be written as mcp into under root T3 whole square minus 2 root T1 root T3. You can write T1 power 1 by 2 as root T1, T3 power 1 by 2 as root T3. So 2 times it is there. So we are writing 2 root T1 root T3 plus root T1 whole square. So this is in the form of a square minus 2ab plus b square. So the maximum work done will be mcp into under root T3 minus under root T1 whole square. So this is the formula for maximum work done. The next point is, if the Brayton cycle operates between minimum and maximum temperatures of T1 and T3 respectively, then for the maximum work done, the intermediate temperatures T2 and T4 will be, see here we know that T2 is equal to T1 into Rp to the power gamma minus 1 by gamma. So for maximum work done, Rp becomes Rp optimum. So therefore we can write this as T1 into T3 by T1 whole to the power gamma by 2 into gamma minus 1 whole power gamma minus 1 by gamma. So these two will get cancelled. So from this we can write T1 into T3 power 1 by 2 T1 power minus 1 by 2. So we can write this as T2 is equal to T1 power 1 by 2 T3 power 1 by 2, or T2 temperature will be under root of T1 T3. Now we got T2 value. Similarly, let us see what is T4. So T4 is equal to T3 by Rp to the power gamma minus 1 by gamma. So we can write this as T3 by T1 whole to the power gamma by 2 into gamma minus 1 whole power gamma minus 1 by gamma. So these two will get cancelled. So from this we can write T3 into T3 power minus 1 by 2 T1 power 1 by 2. So therefore T4 will be equal to, so we can write this as T1 power 1 by 2 T3 power 1 by 2, or under root of T1 T3. So that means here if we take the TS diagram, process 1 to 2 is isentropic compression, 2 to 3 is constant pressure heat addition, 3 to 4 is isentropic expansion, and 4 to 1 is constant pressure heat rejection. So when we come across maximum work done condition, then only T2 is equal to T4, which is equal to under root of T1 T3. Only for maximum work done condition this is correct. Otherwise T4 will be greater than T2 in normal cases. Only for the maximum work done condition this will be more. Now let us go for the next point. The thermal efficiency will be thermal efficiency is 1 minus 1 by Rp to the power gamma minus 1 by gamma. See, for maximum work done we need to write Rp as T3 by T1 whole to the power gamma by 2 into gamma minus 1. That means we need to replace Rp with Rp optimum for maximum work done condition. So therefore these will get cancelled. We can write this as 1 minus T1 power 1 by 2 by T3 power 1 by 2. So therefore the thermal efficiency for maximum work done will be 1 minus under root of T1 by T3. So this is for maximum work done. For maximum, if isentropic efficiencies of the compressor and turbine are given, then what happens? So in order to understand this isentropic efficiency concept, first of all let us see the gas turbine power plant basic diagram. So let me consider there is a compressor. I am taking the block diagram here. So there is a compressor like this. So to the compressor air enters. Air is entering, let us say at condition 1. Now in the compressor air gets compressed and comes out like this at condition 2. Now this compressed air enters into a combustion chamber. So in the combustion chamber usually fuel will be injected, and as a result of that combustion takes place in practical cycles. But when it comes to ideal cycle, let us say during process 2 to 3 heat is added at constant pressure. So at constant pressure heat is added such that the temperature increases and pressure remains constant here. Here let us assume that the compression is isentropic at the beginning. Now this heated air enters into a turbine. This heated air enters into a turbine, where in the turbine expansion takes place. So let us say the expansion that is happening is isentropic expansion. So entropy remains constant during expansion. Then if we consider this power plant as a closed cycle power plant, then we need to close this cycle by using a heat exchanger. If this is an open cycle gas turbine, the exhaust gases will be let out into the atmosphere and fresh air enters. So try to understand, there will be two different types of turbines. One is open cycle gas turbine, second one is closed cycle gas turbine plant. So when it is open cycle gas turbine plant, this will be the plant. When it is a closed cycle condition, then what we need to do is we need to use a heat exchanger. This is ideal case. So in this heat exchanger, from process 4 to 1, heat will be rejected at constant pressure. So heat will be rejected at constant pressure. So this is the ideal cycle that we have considered, and this is a closed cycle gas turbine plant. Now here let us see some important aspects. If you observe closely here, each component of this power plant can be considered as a system. Suppose if we consider only this compressor as our control volume, now fluid is entering into the system and leaving the system. So therefore mass entering the system and leaving the system, and at the same time energy enters the system and leaves the system. So this can be considered as a open system. So when we considered an open system and the process is isentropic compression happening, now the work input that is required for compression, can be written as gamma by gamma minus 1 into P2 V2 minus P1 V1. So this is the work required for compression. Or we can write this work required for compression in another way also, that is by applying the steady flow energy equation here. So let us consider H1 is the enthalpy with which air is entering into the system. So H1 is the enthalpy with which air is entering into the system. So as the process is isentropic process, there will be no heat loss, and let us assume that there is negligible variation in the kinetic and potential energies. So when there is negligible variation in kinetic and potential energies, we can neglect them, and during isentropic process heat transfer is 0. Therefore we can write H1 is equal to H2 minus the work input that we are giving to the compressor. So from this, work input to the compressor can also be written as H2 minus H1. So we can use this formula for work done or this formula for work done. So this is work input that is given to the compressor by considering a control volume approach or by using the formulas of open system. See, try to understand here. So previously when we have learnt about auto, diesel and dual cycles, there we have come across closed system. But here when we are talking about gas turbine plants, we are talking about open system here. So by using open system formulas only we have to solve. That means here we need to consider for compression VDP work and for expansion minus integral VDP work. So that is what we are using here. So try to understand, dear students. Now let us consider this combustion chamber also as a control volume or open system. So here H2 is the enthalpy with which air enters the combustion chamber. So this air gets heated at constant pressure. Let us consider Qs as the amount of heat supplied. As a result of that, the temperature increases at constant pressure. As the temperature increases, internal energy increases. So as the internal energy increases, we know that H is equal to U plus PV, and H is equal to U plus PV. As the internal energy increases, enthalpy also increases, even though pressure is kept constant. Now, so from this we can write the amount of heat supplied Qs is equal to H3 minus H2. So this is the heat supplied formula. Now this air, after getting heated up at a higher enthalpy H3, enters into the turbine. So in this turbine, isentropic expansion takes place, As a result of this isentropic expansion, the enthalpy decreases due to drop in pressure as well as temperature, and as this is isentropic process, heat losses will be zero to the surroundings, and there will be certain amount of work output from the turbine. So this work output from the turbine Wt can be written as H3 minus H4 in terms of enthalpies, or as this is an open system, we can write work developed by the turbine also as gamma by gamma minus 1 for isentropic process into P3 V3 minus P4 V4. This is also correct for the work developed by the turbine. Now, after expansion in the turbine, the air enters into the heat exchanger. In the heat exchanger, at constant pressure, heat is rejected to the surrounding atmosphere. So therefore, if we write the expression here, H4 minus the amount of heat rejected is equal to H1. So this can also be written as heat rejected QR is equal to H4 minus H1. So this is the amount of heat rejected. Now we have got all the formulas of work input to the compressor, heat supplied, heat rejected, and everything. And in this particular case, we have considered the compression and expansion to be isentropic. That means if I draw the TS diagram here, for this closed cycle gas turbine plant, process 1 to 2 is isentropic compression, 2 to 3 is constant pressure heat addition, 3 to 4 isentropic expansion, and 4 to 1 constant pressure heat rejection. So far we have considered the Brayton cycle only. Now see here, if isentropic efficiencies of compressor and turbine are given, that means if isentropic efficiencies are given in the problem, then we need to understand that the process is no more isentropic during compression and expansion, but it follows adiabatic path. That means there will be an increase in entropy during compression, as well as there will be an increase in entropy during expansion from 3 to 4 dash like this. So that means if isentropic efficiencies are given, we need to understand that the process that is happening during compression as well as expansion will no more be isentropic. Instead, it becomes adiabatic. So process 1 to 2 is representing isentropic compression, which is a reversible process. So isentropic compression, the work input that we are giving to the compressor is the ideal work input, that is H2 minus H1, which is also written as gamma by gamma minus 1 into P2 V2 minus P1 V1. So this is ideal work input, or instead of this gamma by gamma minus 1, we will write like this in terms of specific heats and temperatures. We can also write this. So that is mCp T2 minus T1. This is isentropic compression formula. Whereas process 1 to 2 dash, this is adiabatic compression. This adiabatic process is an irreversible process. So the work input that we are giving during as adiabatic compression is the actual work input. So the actual work input should be H2 dash minus H1 which will be taken as mcp into T2 dash minus T1. So this is adiabatic compression. Adiabatic process is irreversible, as I already told you, whereas isentropic process is reversible adiabatic. This is reversible process. Now, isentropic efficiency relates these two compression processes. So isentropic efficiency of the compressor will be work input that is required during an ideal process by WC actual. So you may get a doubt here, sir, usually we should write actual by ideal. Why we are writing ideal by actual in this particular case? See, here try to understand carefully. Compressor is a work consuming device. So ideally it has to consume less amount of work, but due to practical reasons like certain irreversibilities like heat losses due to friction, then magnetic hysteresis, all these are the irreversibilities. Because of these irreversibilities, the actual work that is consumed by the compressor will be greater than the ideal work. So to understand this concept, you just see your refrigerator that is in your home. So in the refrigerator, what is said here? So in the refrigerator, ideally they will say that this refrigerator consumes only 1 watt per day, for example. But practically, if you observe, because of certain atmospheric conditions and certain losses in our house or in the compressor, what will happen? There will be some internal irreversibilities, external irreversibilities. Because of that, the work that is consumed by the compressor of the refrigerator will be higher. So therefore, the actual work consumed by that refrigerator will be more than the company specified things, because see, the testing of the refrigerator, all these will be done under showroom conditions or under lab conditions, but practically the atmosphere that is available will be different. So that's why the actual work that will be consumed by those compressors will be higher. So that is the reason we are writing ideal by actual here. Now from this, ideal work done is H2 minus H1 by actual work input is H2 dash minus H1. We can also write this as T2 minus T1 by T2 dash minus T1. So this is the isentropic efficiency of the compressor. Now let us go for the turbine case. So if you observe the turbine case, process 3 to 4 is isentropic expansion, which is an ideal process. So when we have come across this isentropic expansion, work developed by the turbine will become the ideal work output. So this ideal work output will be H3 minus H4, or you can write this as MCP T3 minus T4. This is the ideal work output. But the actual process is from 3 to 4 dash. This is adiabatic expansion, which is an irreversible process. So when we have considered this adiabatic expansion, WT actual will be H3 minus H4 dash, which will be MCP T3 minus T4 dash. So this is the actual expansion that is happening. Now the isentropic efficiency of the turbine will be WT actual by WT ideal. So here we need to consider actual by ideal. Actual thing is MCP T3 minus T4 dash by MCP T3 minus T4. This is ideal condition. So these two will get cancelled. We can write this as T3 minus T4 dash by T3 minus T4, or you can write this as H3 minus H4 dash by H3 minus H4. See, turbine is a work producing device. So compressor is work consuming device and turbine is work developing device. See, ideally the turbine should develop more work, but practically due to some losses, the work that is developed by the turbine will be lesser. So that's why actual work will be less than the ideal work. So that is the reason we need to consider like this. Now try to understand here, dear students, when isentropic efficiencies of compressor and turbine are given, then we need to know certain things. We need to consider work consumed by the compressor actual, which is H2 dash minus H1 or MCP into T2 dash minus T1. Then work developed by the turbine actual. So work developed by the turbine actual is H3 minus H4 dash, which is MCP into T3 minus T4 dash. Then heat supplied also we need to consider actual. See, heat supplied actual will be, try to understand here carefully, dear students. Ideally heat supplied is H3 minus H2, but if you observe the diagram, actual heat supplied is from 2 dash to 3 when isentropic efficiencies are given in the question. So 2 dash to 3 means we need to consider actual heat supplied as H3 minus H2 dash, or you should take this as MCP T3 minus T2 dash. Then see, the work that is developed by the turbine, we call it as gross work developed, whereas the work developed by the turbine minus work input that is given to the compressor, we call it as the net work output. The reason is, see here, in the cycle if you observe, turbine is developing certain amount of work output. See, that work that is developed by the turbine, we call it as the gross work developed, but this turbine has to supply certain amount of work input to the compressor by using certain shaft. So the net work done will be WT minus WC. So WT minus WC will be the net work output. So therefore net work done also we need to take the actual condition. So net work done actual is nothing but WT actual minus WC actual. So therefore finally the thermal efficiency will be the net work done actual by heat supplied actual. So this will give us the thermal efficiency. And remember that when isentropic efficiencies are given in the problem, you should not use thermal efficiency as 1 minus 1 by Rp to the power gamma minus 1 by gamma. So this formula is wrong when isentropic efficiencies are given in the question. So you should use this particular formula in order to determine the thermal efficiency when isentropic efficiency. The methods of improving performance of a gas turbine plant. So in this, the first one is intercooling, second one is reheating. See, third one is regeneration. So these three are very, very important conditions which we need to consider. So in order to learn about these in detail, so first of all what we need to know is what is this intercooling. So intercooling means this is employed between two compressors. So this will be just like a heat exchanger which will be employed between the two compressors, or when it comes to gas turbines we will be using only two compressors, but in some cases if you go for air compressors, so there you will have multiple compressors where this intercooling is also an important condition. Then reheating. So this reheating is employed in between two turbines. This also is just like a heat exchanger or some additional heat addition device, so that we will be using. Then the third one is regeneration. So these three devices we will be using in order to improve the performance of this gas turbine plant here. Now first of all let us see the intercooling. What is this intercooling? So to consider this intercooling, as I earlier told you that this is employed in between two compressors. So the reason why we are going for two compressors here is in order to get a higher pressure ratio. Excuse me. In order to get a higher pressure ratio we are going to use two compressors, because we can't directly compress excuse me, air from 1 bar to some 60 bar or 70 bar using a single compressor. So if we have to compress the air from 1 bar to 60 bar or 70 bar, the pressure ratio should be 60 or 70, which is not possible for any compressor. So what we need to do is we need to go for compression by stages. So that's why we need to go for multi-stage compression. So in the multi-stage compression what happens is, initially we will be considering a compressor like this. So this compressor we call it as low pressure compressor, LPC, let us say. So into this low pressure compressor air enters at condition 1 and then gets compressed and comes out at condition 2, let us say. Now this air enters into a device called intercooler here. Now from this intercooler it comes out by rejecting heat at constant pressure. So heat will be rejected at constant pressure in the intercooler such that the temperature drops and further this air can be compressed. So here the air is further compressed in another compressor, and this compressor we call it as high pressure compressor. So in this high pressure compressor air gets compressed and comes out at condition 4, and now this enters into the combustion chamber. So in the combustion chamber at constant pressure heat is added, and as a result of that the temperature increases, and now this high temperature and high pressure air enters into a turbine. Now this enters into a turbine where expansion of the air takes place, and this comes out at condition 6. See, the output that we are going to get from the turbine, we call it as the gross work output or work developed by the turbine. So this turbine has to supply certain amount of work input to both the compressors. So therefore the net work output will be work developed by the turbine minus work input to both the compressors. Now here, if I draw the TS diagram, here for this particular case, process 1 to 2 is isentropic compression, let us assume. Then 2 to 3 is constant pressure heat rejection. So constant pressure heat rejection, it comes down like this. Then 3 to 4 is isentropic compression again. And 4 to 5 is constant pressure heat addition. 5 to 6 is isentropic expansion in the turbine. And 6 to 1 is constant pressure heat rejection. So this is constant pressure process, intercooling is constant pressure, and this is also constant pressure. So if we want, we can close this by using a heat exchanger, and we can assume this as a closed cycle plant also. Now let us take the work input to the low pressure compressor. This work input to the low pressure compressor is H2 minus H1. This is the ideal work input. Then work input to the high pressure compressor, the ideal work input will be H4 minus H3. Then the work developed by the turbine ideal will be H5 minus H6. So this is work developed by the turbine. Now here, as I told you earlier, as we are using two compressors, the overall pressure ratio is increasing. As a result of overall pressure ratio increase, so there will be increase in the gross work output compared to that of Brayton cycle. So the gross work output increases, but as we are using two compressors in order to get higher pressure ratio, the net work output may slightly be more than the Brayton cycle, but the heat supplied is increasing compared to the Brayton cycle. If you use a normal Brayton cycle, what happens is, if we use normal Brayton cycle, this will be isentropic compression, then heat addition starts from this point, to here, and then expansion takes place. But here, because of heat rejection in the intercooler and again compression, we need to additionally supply more amount of heat in this particular case. As a result of more amount of heat addition, the thermal efficiency will not increase compared to that of Brayton cycle. So in this particular condition, intercooling, we were able to improve the pressure ratio to a greater extent, but we were not able to improve the thermal efficiency even though the gross work output is increasing. So the heat supplied here will be H5 minus H4 or MCP T5 minus T4. So this is MCP T5 minus T6 here. You can write this as MCP T4 minus T3 and this as MCP T2 minus T1. So these are the work done and heat supplied. Now the thermal efficiency will be net work done by heat supplied. So net work done will be work developed by the turbine minus of work input to the low pressure compressor as well as work input to the high pressure compressor. So this total divided by heat supplied. So this will give us the thermal efficiency for this particular condition. See here the gross work output is increasing due to intercooling, but thermal efficiency is decreasing compared to that of Brayton cycle. The reason is that heat supplied is more than the Brayton cycle heat supplied. So that's the reason thermal efficiency decreases in this particular case. Now here we need to learn one important thing called perfect intercooling. So what do we mean by this perfect intercooling? Let us see. So when we come across this perfect intercooling, the temperatures at the entry to both the compressors should be same. That means the temperature at which air is entering into the low pressure compressor, let us say this is T1, and temperature at which the air is entering the high pressure compressor, this is T3. So in perfect intercooling condition, the temperature at entry to both the compressors should be same. So that means T1 must be equal to T3 when we talk about perfect intercooling. So in order to have this perfect intercooling, the pressure ratios in both the compressors should be same. So that means the pressure ratio in the first compressor is P2 by P1. This will be equal to, see, pressure ratio in low pressure compressor is P2 by P1, whereas pressure ratio in the high pressure compressor is P4 by P3. So for perfect intercooling, the pressure ratio in both the compressors should be same. That means, as we know that process 223 is constant pressure intercooling, at constant pressure intercooling takes place. So P2 must be equal to P3. So when P2 is equal to P3, then this will be under root of P1 P4. So in order to have perfect intercooling, we need to have that the intercooler pressure should be the geometric mean of the maximum pressure and the minimum pressure of the cycle. So try to understand here carefully. The maximum pressure of this cycle is P4 equal to P5, whereas the minimum pressure is P1 is equal to P6. So in order to have perfect intercooling, the intermediate pressure, that is P2 equal to P3 here. So this P2 equal to P3 must be the geometric mean of maximum pressure of the cycle and minimum pressure of the cycle. So this is the important thing that we have to learn for perfect intercooling. So perfect intercooling means the temperature at the entry to both the compressors should be same. Then only we can say that the intercooler is a perfect intercooler. This is about the intercooling process. So try to remember this, dear students. So during intercooling, the thermal efficiency will be decreasing compared to that of Brayton cycle because of more amount of heat addition, even though there is an increase in the gross work as well as net. So in this reheating, we will be using only one compressor, but here we will be using two turbines. So let us consider there is a compressor like this, into which air is entering at condition 1, and process 1 to 2 is isentropic compression happening. Let us say 1 to 2 is isentropic compression. Then this air enters into the combustion chamber here. So air enters into the combustion chamber, and at constant pressure the temperature increases to condition 3. Now this air enters into a turbine, and here we named this turbine as the high pressure turbine. So this is high pressure turbine here. The reason is the pressure after compression will be highest. So that's why we have considered this turbine as the high pressure turbine based on the entry condition pressure. So here P2 equal to P3, which is the highest pressure of the cycle. So that's why at highest pressure air is entering into the turbine. This turbine is named as high pressure turbine. Now in this high pressure turbine, air gets expanded from 3 to 4 and enters into a device called reheater here. So in the reheater, at constant pressure heat is added. At constant pressure heat is added from 4 to 5, and with this highest temperature, because of reheating, air enters into another turbine called low pressure turbine, because the entry pressure at condition 5 is less than the entry pressure at condition 3. So P3 is greater than P5. That is the reason we named this turbine as high pressure turbine and this turbine as the low pressure turbine. So in the low pressure turbine, isentropic expansion takes place from 5 to 6 like this, and at condition 6 this enters into a heat exchanger if this is a closed cycle, or if it is an open cycle, this will be let out into the atmosphere. In the heat exchanger at constant pressure, heat rejection takes place and this cycle again continues. Now in this particular reheating concept, whatever is the power that is developed by the low pressure turbine, that power we call it as net power. The reason is here, whatever is the work developed by the high pressure turbine, that is completely utilized by the compressor. So that means whatever is the work input that is required for the compressor, that will be totally supplied from the high pressure turbine, and whatever is the output that is coming from the low pressure turbine, that will be completely available for further utilization. That's why the net power output is the power that is developed by the low pressure turbine here. Now let us draw the TS diagram here. If we draw the TS diagram in this particular case, process 1 to 2 is isentropic compression, 2 to 3 is constant pressure heat addition like this, 2 to 3. Then 3 to 4 is isentropic expansion in the high pressure turbine. So 3 to 4 is isentropic expansion. Then 4 to 5 is reheating in the reheater. This is constant pressure reheating. And 5 to 6 is isentropic expansion in the low pressure turbine. And 6 to 1 is constant pressure heat rejection in the heat exchanger. Now here try to understand carefully. The net work output is equal to work developed by the low pressure turbine, and work input to the compressor is equal to work developed by the high pressure turbine. Here heat supplied will be in the combustion chamber. The total heat supplied will be heat supplied in the combustion chamber as well as heat supplied in the reheater. Heat supplied in the reheater. So therefore the thermal efficiency will be net work done by the total heat supplied. So that means net work done by heat supplied in the combustion chamber as well as heat supplied in the reheater we need to consider. Now try to understand here, dear students, carefully that even though there is an increase in the net power output, the thermal efficiency in this case also decreases because of additional heat supplied in the reheater. So here, as the heat supplied is also increasing, even though there is an increase in the net power output, the thermal efficiency decreases. So this is the case of reheating here. So in both intercooling and reheating, the thermal efficiency is decreasing even though there is an improvement in the work output because of more amount of heat additions. Now let us see the formulas of work developed by or work input to the compressor. This is H2 minus H1. This is equal to mCp T2 minus T1. Work developed by the high pressure turbine. This will be H3 minus H4, which can be written as mCp T3 minus T4. And work developed by the low pressure turbine is equal to, so work developed by the low pressure turbine is H5 minus H6. So this is mCp T5 minus T6. Heat supplied in the combustion chamber. Heat supplied is during process 2 to 3. So H3 minus H2 or mCp T3 minus T2. This is heat supplied in the combustion chamber. And heat supplied in the reheater. So reheating is happening from 4 to 5. So H5 minus H4, you can write this as mCp T5 minus T4. So this is heat supplied in the reheater. So these formulas we need to remember. Apart from this, we need to also know about what is perfect reheating condition. So coming to this perfect reheating, so in order to have perfect reheating, the pressure ratios in both the turbines should be same. So pressure ratios in both the turbines should be same means P3 by P4 must be equal to P5 by P6. So P3 by P4 must be equal to P5 by P6. So that implies in the reheater pressure is remaining constant. So P4 is equal to P5. This will be under root of P3 P6 or under root of P1 P2. So why we have written like this is, try to understand here carefully. P2 is equal to P3 and P6 is equal to P1. The intermediate pressure or the reheater pressure is P4 equal to P5. So this P4 equal to P5 will be the geometric mean of the maximum pressure and minimum pressure of the cycles. So then only the perfect reheating condition can be obtained. That means perfect reheating has happened is indicated by these temperatures P3 and P5, sorry, T3 and T5. If T3 is equal to T5, then we can say that perfect reheating has happened. So that means the temperature at entry to both the turbines should be same. So when temperature at entry to both the turbines is same, then we can say that this is perfect reheating. So when it comes to this regeneration, we are not going to use any additional compressor or turbine. So let us consider there is a compressor like this. Now process 1 to 2, let us say this is isentropic compression taking place. Now from this compressor, air enters into a combustion chamber where heat is added at constant pressure like this. Then this air comes out from the combustion chamber and enters into a turbine. Now in this turbine the air gets expanded, and after expansion also, as we know that T4 temperature is greater than T2 temperature, this air that is coming out from the turbine is having a higher temperature compared to the temperature at the entry to the combustion chamber or from the exit of the compressor. So what we are going to do is, in order to utilize this temperature, we will be using a device called regenerator here. So this regenerator is nothing but a heat exchanger. This regenerator is placed in between the compressor and the combustion chamber, and in this regenerator or heat exchanger, what happens is, at constant pressure, from this condition 4, or from the exit of the turbine, the air will be coming out. This air exchanges heat with the air that is leaving the compressor. So here, because of the exchange of heat by the air that is coming out from the turbine, the temperature of air that is entering into the combustion chamber increases. So what is happening here is, if we draw the TS diagram, here, process 1 to 2 is isentropic compression. See, 2 to A, the temperature of the air is increasing because of the exchange of heat in the regenerator, and this 2 to A process is not external heat supplied, it is just utilization of heat. It is just utilization of heat, or effective utilization of heat, that is usually lost. So what we are doing is, simply we are effectively utilizing that heat in order to heat the air that is entering into the combustion chamber. So when we have used this heat that is entering into the combustion chamber, from A to 3, this is the actual amount of heat supplied. So this will be the actual amount of heat supplied. So if you observe carefully, in the normal Brayton cycle we used to supply heat from 2 to 3 process, but in this regeneration concept we are supplying only heat from A to 3. That means the amount of heat supplied that we are giving is reducing because of effectively utilizing the heat that is going as waste from the turbine. So as a result of that, as the heat supplied is reduced, the thermal efficiency improves. So process 3 to 4 is isentropic expansion in the turbine, and 4 to B, this is heat rejection in the heat exchanger or the regenerator. This point is B here. Now we can place another additional heat exchanger, and at constant pressure we can close the cycle. So from 6 to 1 we can close the cycle like this. So here the net work that is developed will be the turbine work minus compressor work. So net work done will be turbine work minus the compressor work, and heat supplied will be from A to 3 process. So therefore let us write the formulas here. Work developed by the turbine will be H3 minus H4, that is equal to mCp T3 minus T4, and work input to the compressor is H2 minus H1. This is equal to mCp T2 minus T1. See, up to here this is same like the Brayton cycle, but when it comes to heat supplied in the combustion chamber, heat supplied is during process A to 3. So therefore here we can write this as H3 minus HA or mCp T3 minus TA. mCp T3 minus TA. Now the thermal efficiency is net work done by heat supplied. So net work done is turbine work minus compressor work by the amount of heat supplied. Now the question that arises here is, we can find T2, we can find T4 because the processes are isentropic process. If pressure ratio is given, T2 can be determined by using T1 into Rp to the power gamma minus 1 by gamma. So T2 can be determined like this. T4 can be determined by using T3 by Rp to the power gamma minus 1 by gamma, if T3 and pressure ratio are given, minimum and maximum temperatures. But how do we determine this TA? This plays a very important role here. So as TA is required, we need to know about a small concept that is related to heat exchanger efficiency. So the efficiency of the heat exchanger or efficiency of the regenerator that we are using here. So efficiency of the heat exchanger or efficiency of the heat exchanger. So the heat exchanger that we are using here is like this. So this is a heat exchanger that we have used. This is the regenerator. So in the regenerator, one fluid is flowing from 2 to A in this direction like this, and the other fluid is flowing in the opposite direction from 4 to B like this. So this, in the heat exchanger, heat is lost by the fluid that is moving from 4 to B. So if you observe, both fluids are flowing in the opposite direction. We can consider this as a counterflow heat exchanger and draw the temperature versus length diagram. So from 2 to A there is a rise in temperature. This is T2 and this is TA, and from 4 to B there is a drop in temperature. So T4 to TB like this. Now the efficiency of the regenerator or efficiency of the heat exchanger will be actual heat transfer to the maximum possible heat transfer. Q actual by Q max will give us the efficiency of the heat exchanger. The actual heat transfer will be heat lost by the hot fluid or heat gained by the cold fluid. So here hot fluid is the fluid that is flowing from 4 to B, whereas the relatively cold fluid is the fluid that is flowing from 2 to A. So therefore we can write actual heat transfer as heat lost by hot fluid, that is mCp T4 minus TA, T4 minus TB, or we can also write this as mCp TA minus T2. This is heat gained by the cold fluid. So heat lost by hot fluid or heat gained by cold fluid, or divided by maximum heat transfer. So the maximum heat transfer Q max will be equal to mass into specific heat multiplied by the maximum temperature difference. So maximum temperature difference is from T4 to T2. So T4 minus T2 is the maximum temperature difference. So we can write this as mCp T4 minus T2. So MCP T4 minus T2 we need to consider as the maximum possible heat transfer. See, in order to have maximum possible heat transfer, we need to have maximum temperature difference. So maximum temperature difference, delta T max, is nothing but maximum temperature minus minimum temperature of the heat exchanger. Maximum temperature is T4 and minimum temperature is T2. So that's why we have written T4 minus T2. So the regenerator efficiency or efficiency of the heat exchanger can be written as so here T4 minus TB by T4 minus T2, or efficiency of the regenerator or heat exchanger. This will be equal to TA minus T2 by T4 minus T2. See, this efficiency of the regenerator is also called effectiveness of the regenerator. So sometimes in the questions he will be saying effectiveness of the regenerator is also called the efficiency of the regenerator. So if he says effectiveness, don't consider that it is some other term. So if effectiveness of the regenerator or efficiency of the regenerator is given, then by using that particular efficiency or effectiveness, you can determine the TA temperature. So by using this particular formula, so come across this perfect regeneration, then effectiveness will be equal to 1. Otherwise, effectiveness will be always less than 1. So for perfect regeneration, effectiveness must be equal to 1 here. So when effectiveness is equal to 1, effectiveness is TA minus T2 by T4 minus T2. So this implies when effectiveness will be equal to 1, then TA must be equal to T4. Or if effectiveness is written like this, T4 minus TB by T4 minus T2, then TB will be equal to T2. So this happens when we have taken perfect regeneration condition. Perfect regeneration means effectiveness is equal to 1. But in the normal cases, effectiveness will be always less than 1. Only for perfect regeneration, try to remember that effectiveness will be equal to 1. Now, when we considered perfect regeneration condition, then the thermal efficiency is net work done by heat supplied. Net work done is turbine work minus compressor work by heat supplied. So turbine work is MCP T3 minus T4 minus compressor work is MCP T2 minus T1. This is compressor work by the amount of heat supplied is MCP T3 minus TA. So here heat supplied is MCP T3 minus TA. A23 is the heat supplied process. Now if you observe carefully, MCP gets cancelled everywhere, and for perfect regeneration, T4 is equal to TA for perfect regeneration condition. So that is what we have learned. For perfect regeneration, when effectiveness is equal to 1, TA will be equal to T4. So in that particular case, we can write this as T3 minus T4 minus T2 minus T1 by T3 minus T4, or we can write this as 1 minus T2 minus T1 by T3 minus T4. Now T1 is the minimum temperature of the cycle and T3 is the maximum temperature of the cycle. Suppose if we write, or if we take T1 common in the numerator, then this becomes T2 by T1 minus 1 by, in the denominator, if we take T3 common, so if we take T3 common, 1 minus T4 by T3 will be there. So this is what we have written. Now see process 1 to 2. Process 1 to 2 is isentropic compression. So we can write this as PV power gamma equal to constant. From this, T2 by T1 is equal to P2 by P1 whole to the power gamma minus 1 by gamma. See, P2 by P1 is nothing but the pressure ratio. This will be Rp to the power gamma minus 1 by gamma. So T2 by T1 can be written as pressure ratio. So 1 minus T1 by T3, let us write like this. In the numerator, Rp to the power gamma minus 1 by gamma minus 1 divided by 1 minus T4 by T3. So let us go for process 3 to 4. So process 3 to 4 is isentropic expansion in the turbine. So PV power gamma equal to constant. So from this we can write T3 by T4 is equal to P3 by P4 whole to the power gamma minus 1 by gamma. P3 by P4 is nothing but the pressure ratio, that is Rp to the power gamma minus 1 by gamma. See, try to understand how we have written these pressure ratios. See, pressure ratios are obtained from this diagram only. In the turbine, isentropic compression is taking place, isentropic expansion is taking place, and in the compressor, isentropic compression is taking place. See, the maximum pressure of the cycle is P2 equal to P3 and the minimum pressure is P4 equal to P1. So that's why the compression ratio, the pressure ratio will be P2 by P1 or P3 by P4. The pressure ratio will be P2 by P1 or P3 by P4, because process 2 to 3 is constant pressure and process 4 to 1 is also constant pressure. In the heat exchanger and everywhere the pressure is kept constant. Now by using this particular case, we can write this as 1 minus 1 by Rp to the power gamma minus 1 by gamma. So this is how we have written. Observe this carefully. The thermal efficiency can be written as 1 minus minimum temperature by maximum temperature into Rp to the power gamma minus 1 by gamma minus 1 divided by, if we take LCM, Rp to the power gamma minus 1 by gamma minus 1 by Rp to the power gamma minus 1 by gamma. This is what we have got. So these two gets cancelled, and finally the thermal efficiency can be written as 1 minus T1 by T3 into Rp to the power gamma minus 1 by gamma. So this is the thermal efficiency. So this formula stands good when effectiveness is equal to 1 or perfect regeneration condition. So for perfect regeneration, effectiveness will be equal to 1. That means the regenerator that we are using is 100% efficient. So then only we can